We're going to pick up where we left off, which is identifying domain and range of each of the 8 parent functions that we learned in class. So we'll go ahead and we'll do domain. So when you're looking at domain, remember you look left to right. So what you need to know is, even though you can't see them, there are arrows on here. We just typically don't draw them in the textbook or on worksheets just because it's extra stuff. So unless they actually put a physical dot, assume there's arrows on the graph. All right, so this line goes forever and ever and ever to the left. So we're going to say it starts with negative infinity. Right, so it just goes to the left forever. And then it continues to flow all the way to the right forever. So your domain would be all reals. And then your range, again, you want to look at the lowest point on your graph, which is right here, and that's at 0. So we're going to say 0. You want to use a bracket because it is colored in. It's a solid dot at 0. So if you don't see a dot, then it's definitely going to be a bracket anyway. And the graph just goes up forever. So my range is going to go to infinity. Letter B. Again, we're going to start with domain here. So right here, there is a point for the square root function right here at 0. So it's going to start at 0. And it's going to go forever to the right. So you're going to say infinity. And then for the range, the lowest point is still here at 0. And it does go up forever, so it'll keep going up and up and up and up. So it's also to infinity. Letter E, the cubic function. So again, we're going to start with domain. So the key of this problem is realizing there's arrows in both directions. So it's going to go left forever. So that means we're going to write negative infinity. And it's going to continue to go to the right, and it's never going to stop. And it's the exact same thing with the range. It goes down forever, and it just continues to rise and rise and rise without ever stopping. So what I'd like you to do is just pause the video and go through and see if you can do domain and range for the remaining parent functions, and then you can unpause and check your answers. So go ahead and take a look here. Letter F should have been the same as letter E, right? Goes on forever, top, bottom, left, right. On letter C, in terms of left to right, it's negative infinity to infinity, but the range is strictly 1, so there's no other height in this range. It starts at 1 and it also ends at 1, so we just kind of use brackets and we just write the number 1. And then for the exponential function, right, so it goes on to the left forever, it goes on to the right forever, and your range, however, the lowest point on the graph would be above 0. So it gets closer and closer to 0, but it doesn't ever actually get there. And then letter G is similar to what we did prior in some of the other videos. So we have, it's going left forever, and then it kind of tailors off at 0, and then it kind of picks up after 0, and then it goes forever to the right. So that's why we need the union symbol, and it's the same thing for the range. We're going to switch gears now, and instead of talking about domain and range, we're going to be talking about comparing transformations of parent functions. So it says to identify the function family. That means what parent function are we talking about? And then you're supposed to graph or compare this graph to the graph of the parent function. So what I would do first is I would go ahead and specify that this is a linear function, right? It's a line. And then I would graph the parent function for a linear function, which is f of x equals x. And then your job is to just basically compare this new function to the parent function. So it looks like they took the parent function and they did a couple things. So the first thing they did was they kind of made it less steep, and that's called a vertical shrink. So definitely the parent function is steeper than the new function. They also took this line and they shifted it up 8 units, so 2, 4, 6, 8. So that's something else that happened. And then they also kind of flipped it across the y-axis. So we call that a reflection. Number 2 obviously is a constant function. And we're just going to go by what our textbook says. I don't think there's a definite certain point you have to graph the parent, but your textbook does it at 1, so we'll graph the parent function at 1. So the transformation based on that fact is they took this parent graph and they shifted it down, and that's how we get to the new graph. So that's what it means when it says compare. You're just basically telling us what happened to the graph. So number 3, if you remember, the v is an absolute value function. And the original graph for an absolute value looks like this. So you can see that this got much steeper. It got much more narrow in the middle, and that's called a vertical stretch. So if it gets steeper or more narrow towards each other, that's called a stretch. And then whatever number is in front of x, that's called the factor. So we'd say this is a vertical stretch by a factor of 5. Last but not least, we have a quadratic function with several transformations to it. So this is what your normal quadratic function looks like. So you need to try to figure out what happened to get from here to here. So it looks like it went up and right. So we're going to say it shifted up 4 units because it was at 0, and now the bottom's at 4 in terms of height. And it also went 1 space to the right because it's in the middle and each space is worth 2. So this would be at 1 on the x-axis. So we would say there's a horizontal shift right 1 unit. So next they actually want you to graph the new function, which is right here, and its parent function. That way you can kind of see the relationship. So this time you're going to graph both instead of just the parent. So what I would do first is I go through and I graph the parent function. So we'll use, for my PowerPoint, I'm going to use red for parent and blue for transformation. So there's your parent function. It's a linear function, and that's what it looks like. For number 6, your parent function is a constant. So I'm just going to draw a horizontal line through 1. And then obviously your absolute value function is a v through the origin. So I would go ahead and graph my parent functions, get those out of the way. And then we should know how to do 5 without a table. So we're going to start at -7, and we're going to go up 1, right 1. So basically up a half a space, right a half a space, and so on. And then the constant, obviously, it's a horizontal through -9. And then for number 7, you can go ahead and make a table. I'm just going to kind of shortcut that a little bit. If you made a table, your points would end up giving you a graph that looks like this. So now comes the easy part. You just have to tell us what happened. So how did we go from red to blue? So what do you see? So it looks like the red one went down. So we just say it's a vertical shift down, and it's actually going down 7 units. So you could say vertical shift down 7 spaces. So it goes through right here. Same thing with number 6. From red to blue, it went down. So we say it's a vertical shift down. Number 7, however, is a vertical shift up, and it's actually up by 1 unit. We'll talk more about how to figure out the number of units later. Right now, you just need to get the directions down. So what you should do right now is pause the video and go ahead and graph the parent functions for the quadratics and the absolute value. That should be not too bad. And then I want you to graph each of these through making a table. Okay, so make a table and plot 3 or 4 points for each one, and then I want to see how those compare. Okay, so your graph should look like the following. I should see a parabola for 8 and 9 and a V for number 10. And then I should see an upside down parabola, so you should have gotten that from your table, a wider parabola, and a more narrow V. So all that's left is just to simply describe what happened. So for number 8, it is reflected across the x-axis. So it's basically flipped upside down. Number 9, since it got wider, it's less steep, so we call that a vertical shrink. Number 10 is opposite. It got more narrow, so it got steeper, and that's a vertical stretch.